Imagine you decide to open a cozy little coffee shop in your neighborhood. On day one, you have one barista behind the counter. Business is modest, everything is perfect, and every customer gets their coffee fast. But then, your coffee goes viral on social media. Suddenly, hundreds of people rush through the door all at once. Your single barista gets completely overwhelmed, orders are dropping, people are shouting, and eventually your barista just collapses from exhaustion. Your business grinds to a halt. This is exactly what happens to software applications. When you launch your app, a single backend server can easily handle a few hundred users. But what happens during a Black Friday flash sale? Or when a massive piece of news breaks and millions hit your website at the exact same second? Your single server runs out of CPU and memory, slows to a crawl, and crashes. How do we fix this? We can't just keep buying a bigger, more expensive single server forever. That's called vertical scaling, and it has a hard physical limit. Instead, we use horizontal scaling. We buy 5 or 10 regular servers and run them side by side. But this introduces a brand new problem. When a user types in your website URL, how do we decide which server handles their request? How do we stop all the traffic from rushing to server 1 while server 2 and 3 sit completely empty? Enter the unsung hero of modern system design, the load balancer. Think of a load balancer as an expert traffic cop standing right in front of your server farm, or a brilliant flow manager at that busy coffee shop. Instead of letting customers rush the counters haphazardly, the manager stands at the entrance, greets every single customer, and says, "You go to counter A, you go to counter B, and you go to counter C." Take a look at this setup. In professional terms, the load balancer sits directly between the user's device and your backend infrastructure. The user never actually talks to your backend servers directly. They only ever see the public IP address of the load balancer. When a request arrives, the load balancer takes it, analyzes it, and securely hands it off to an available server in the pool. The server processes the request and sends the response back through the load balancer to the user. To the end user, the entire process is completely seamless. By implementing this single component, we instantly unlock 3 massive enterprise benefits. First, high availability. If server A catches fire or undergoes maintenance, the load balancer instantly shifts traffic to healthy servers. No downtime. Second, scalability. Need to handle double the traffic? Just plug in 3 more servers into the pool behind the load balancer. And third, smart performance. It prevents performance hotspots where one server is drowning while others are idling. Now, let's get into the technical core. How does a load balancer actually decide which server gets the next request? It uses specific mathematical strategies called load balancing algorithms. These are broadly split into 2 words, static and dynamic. Let's start with static algorithms. Static algorithms make decisions based on fixed, predetermined rules. They don't care if a server's CPU is currently spiking at 99%, they just blindly follow the playbook. The most famous example is round robin. It works exactly like dealing a deck of cards. Server A gets a request, then server B, then server C, and then it loops back to server A. It is beautifully simple and incredibly fast, making it perfect when all your backend servers have identical hardware power. But what if you have a mixed environment? What if server A is a heavy-duty cloud server with 64 GB of RAM, while B and C are older 60 GB machines? In that case, we upgrade to weighted round robin. As the developer, you assign a weight or priority value to each server. If server A has a weight of 3 and the others have a weight of 1, the load balancer will send 3 consecutive requests to the powerful server A before sending 1 to server B and 1 to server C. This ensures your powerful machines do the heavy lifting. The third major static method is IP hash. Here, the load balancer takes the client's unique IP address, runs it through a mathematical formula called a hash function, and generates a specific server destination. Why do this? Because it guarantees session persistence. If a user is halfway through an e-commerce checkout and has a shopping cart active on server B, you want every subsequent click to land on server B so they don't lose their data. IP hash ensures that as long as your IP doesn't change, you always land on the exact same server. Now let's look at dynamic algorithms. What if some requests take 2 milliseconds to process, while others take 10 seconds to generate a massive report? Static algorithms fail here because they don't look at active usage. That's why we use dynamic algorithms which monitor the live health and state of the servers. The primary dynamic method is least connections. The load balancer keeps a real-time ledger of exactly how many active open connections each server has. When a new request arrives, it looks at the ledger and sends the request to the server that is currently the least busy. This is perfect for video streaming applications or heavy database work where connection durations vary wildly. If you are preparing for a system design interview or a cloud certification, this next topic is an absolute must-know. Load balancers operate at different layers of the network stack, specifically Layer 4 and Layer 7 of the OSI model. Let's break down exactly what this means. Layer 4 load balancers operate at the transport layer. They are blind to the actual content of the request. They cannot read your HTTP data, your cookies, or your URLs. They only look at raw network packages, the source IP, destination IP, and TCP or UDP ports. Think of it like a mailroom sorting packages based strictly on the zip code written on the box. It doesn't know if there is a letter, a book, or a laptop inside. Because it doesn't spend time opening and inspecting the package, Layer 4 load balancing is incredibly fast, highly efficient, and consumes very little CPU power. It's built for raw network speed. On the other hand, Layer 7 load balancers operate at the application layer. This means they are completely application aware. They can unpack the network data and inspect the actual HTTP headers, cookies, form data, and the precise URL path. This allows for content-based routing. Imagine you run a massive entertainment site. A user requests mysite.com/video. A Layer 7 load balancer reads that URL and intelligently routes the traffic directly to a specialized cluster of video streaming servers. If the user clicks mysite.com/checkout, it safely routes them to a highly secure payment cluster. While Layer 7 requires more CPU power because it has to decrypt and inspect the data, it provides unparalleled intelligent control over modern microservice architectures. Beyond just distributing traffic, a production-grade load balancer handles critical automated management tasks. The most vital of these is health checks. A load balancer won't blindly send traffic to a dead server. Every few seconds, it sends a tiny heartbeat request to every server in the pool. Like a quick HTTP ping asking, "Are you awake and healthy?" If a server fails to respond a few times consecutively, the load balancer marks it as unhealthy and completely pulls it out of the rotation. Once the server recovers and passes its health checks again, the load balancer smoothly reintroduces it to live traffic without a single human administrator needing to type a command. Another massive architectural feature is SSL or TLS termination. Cryptographic decryption takes a significant toll on a server's CPU. Instead of making every single backend server handle the math of decrypting HTTPS traffic, we can offload that task directly to the load balancer. The load balancer decrypts the incoming traffic once and passes fast, unencrypted HTTP requests through the secure, private internal network to the backend servers, saving massive compute resources. From managing small websites to keeping global giants like Netflix, AWS, and Google up and running 24/7, load balancers are the fundamental core of reliable system design. They prevent crashes, maximize hardware efficiency, and guarantee that your users experience lightning-fast load times even during massive traffic spikes. If you are looking to implement this in your own projects, you can look into legendary open-source software tools like Nginx and HAProxy, or use cloud-native managed solutions like AWS Elastic Load Balancing or Google Cloud Load Balancing. If you found this deep dive clear and helpful, make sure to hit that like button, subscribe to the channel for more clean system design tutorials, and drop a comment below on what system design component we should break down next. Until next time, happy coding!